Alright, let's quickly crank this one out. This day is Dijkstra's algorithm. If it's a fairly well documented one, other people can explain it way better. So I recommend just go ahead and Google that if you aren't familiar. Otherwise, let's go ahead and start writing it. So for this question, first of all, we get this grid. I'm just going to go ahead and put it into a dictionary. Not because it's more efficient or better, just because I'm going to do it. Let's just do this. First of all, let's make our point, or quote unquote point class. And then here for what? Just to save time, because I've done this like thousands of times. Nope, that's not what I wanted. Here. Alright, so here we're reading our input, we're turning this into an integer, that'll be that. And then also, let's go ahead and, since we need to detect our final kind of end, we'll do shape is equal to len input.split lines. This is basically the square grid, and because we get one test input for part 2, I'm actually just going to read both parts, so we're basically going to do this, input.split lines at 0, -1, shape -1. So we're doing -1 because the length gives us 1 past our index, but this basically will give us the coordinates of our bottom right point. And the whole reason why I'm not just using shape twice is, for part 2, spoiler, we get a test case that is not a square, it's a rectangle. Everything else is a square. Like, as far as I can tell, your input is also a square. So now we have all of this. Now let's go ahead and we'll create a solve function. And it'll take in a part 1 parameter for now. So inside of here, since we're doing Dijkstra's algorithm, we're going to do 2 parts. So first of all, we're going to have a set of scene elements to avoid like our sample space getting huge. And I'll kind of explain this a little bit more. And then we'll also have our queue. And our queue is going to take in some states. And so let's first go ahead and define what our actual states are. So a state is going to be a class we make, def init, and it's going to take in a heat loss, a position, a direction, and how many continuous steps we've made in that direction. So I'm going to go ahead and copy this over, just because it's kind of straightforward. And let me explain. So all of these are copied, and then key is just going to be our position, our direction, and our what's called how many continuous steps we've made. And this is what we're going to be putting in this scene set. And basically what we can do is anytime we see a state that we've already seen, we don't need to process it because we've already been there. So there's that. And then finally, I'm going to define a less than function, which is like this operator. And it's going to take in self and another. Oh. And I'll explain in a second why we need this. But what we're going to do is return self.loss, how many continuous steps we've made, is less than other.loss, other.continuous steps. So basically, I just need some way of comparing less than, and this is used for things like sorting and things like that. And then in our case, we're going to be using it because of heap queue. So heap queue is basically a minimum heap, which if you don't know what that is, don't worry. All it is a data structure that'll quickly give me my minimum element from like whatever my list is, and I can also add things to it. If you want to look more into it, just search up heaps, like min heap, yeah. But yeah. Alright, so now to implement Dijkstra's algorithm, we're going to start off with 2 states. So like this, and let me explain what these mean in a second. Alright, so this is basically saying I start off with no heat loss, I'm at position 0, I'm in direction 1, which is going to the right for complex numbers, and then I've gone 0 continuous steps. And this is the exact same thing, except I'm just going down. Alright, so now that we have all of this, let's go ahead and, first of all, just to be safe, heapify queue. So this function basically just guarantees that this is in a heap, which we kind of need so that it has some properties. I think it's fine if you don't have this, but it doesn't hurt. So I'm just going to have this. Actually, it really does nothing, so I'll just get rid of it. But now here, so while we have stuff in our queue, we'll do s is equal to heap queue.heap pop. So, pop queue. So what this does is it basically gives me the smallest element from my heap and removes it from the heap at the same time. And then now what we'll do is first our caching. So if key in scene, then we can just continue. So you can basically just pop it out of the thing, get rid of it, and then we don't have to process it. And then otherwise this means we haven't seen it. So we'll go ahead and add it here. Alright, so now we'll just extract some of the variables, just make it easier on the code. s.p, s.d, s.c. So these are just the same variables. I just don't want to have to keep typing s dot something. And then so now what we're going to do is our end conditions. So if p is equal to end, return loss. So if we're at the last square, return our loss. And then if p is not in grid, we'll just go ahead and continue. This is just like a little bit of a safety error checking, just to make sure we're not getting anything weird. Or I believe we don't even need this, so we'll comment this out for now. So here, now, what we'll do is, so we'll do this moving straight direction. So if c is less than 3, meaning we've moved less than 3 steps forward, and if we move one more step, it's in grid, and this is why I'm commenting out this. We don't really need this anymore. If this is in grid, then we'll go ahead and heap q.heap push onto our q, which is our q. We'll push a new state where it's grid p plus d, and we're adding this condition so we don't have to deal with out of bounds issues here. So we have this, p plus d, d, c plus 1. So what this is saying is create me a new state, put it onto my heap, where it's the new heat loss for whatever square we entered, the new square we're at, the direction because we're going straight, and then one extra block. So this goes straight. Now let's go ahead and, so I can do this nice little one trick where I can do if, it will do if p plus d in grid, and I already turned this basically clockwise, 90 degrees. If p plus d is in grid, then what we'll do is heap q dot heap push q state loss plus grid p plus d, again d, and then 1. So basically, I change my direction 90 degrees to the right, and I say add it to the grid, and then make sure I've only moved one, like say I've only taken one step so far. Then I'll copy all of this, and I'll multiply this by, I'll rotate it 90 degrees 2 more times in a row, and I times I is -1, so I'll just do that, and then here. So now this is counterclockwise. And then finally, we're returning this out here, so let's go ahead and do solve true for part 1. And let's see what we get. Alright, on the test case we get 102, which is here. And if I go ahead and submit it, let's see what we get. Cool. Alright, so now for part 2. So I'll explain like kind of the catches, but the first thing is you need to move a minimum of 4 blocks. And you need to do this even before you stop at the end. That was the part I did not recognize and I kept failing on. But also you can move a maximum of 10 blocks. So now all we have to do here is we go into here and change a couple of our conditions. So first of all, to reach the end, we either need to be in part 1 or we need to have moved at least 4 blocks. So that case is done. And now here we'll do part 1, it'll be this, or not part 1 and c is less than 10. So now we can move like this. So that takes care of the 10 condition. And then now for here we'll have to do if part 1, so it's either part 1 and it's fine, or we've already moved 4 squares. And then we'll do this. And this is the same condition here. So now if I go ahead and run this on the tests, oh, maybe I should call it. Alright, we get 94 and 71. And if I look here, 94, 71, and then if I submit my code, which takes about 11 seconds, and there, and we're done.